All right, hey, what's up everybody? Mr. Fortin here. I'm going to take you through this video. Now, this should already be in your notebooks because we did it during Thursday's class, but I'll start taking you through the special centers of a triangle. So triangles have many centers to them that give us some things of particular significance. So what I'm going to go through in this video is I'm going to go through the centroid with you. I'm going to go through the incenter with you, and I'm also going to go through something called the circumcenter that we experienced in yesterday's class. So it's a lot to keep track of in geometry and a lot of things to pay attention to in terms of how things connect. But it turns out that the constructions you've been studying right now allow you to find things that allows you to discover more stuff about our triangles. Probably most significantly is one of these special points is the center of gravity, the center of balance. So you can actually balance a triangle like this here. And there are actually other figures have this name too. So beyond triangles, any two-dimensional figure has a centroid. We'll get into centroids later. Here's one that they did in 6 block yesterday. I love this one. It's a very obtuse triangle. This one also has, because they constructed very carefully, a center of balance as well right there. I move it slightly off that construction. What's it going to do? It's going to fall. Okay, so let's just quickly review this from yesterday so we can get into your notes. Make sure you have a nice, about half page, I'd recommend, table just set up like this, 3 rows to a construction, concurrent at, and why is it special? Okay, so let's go through this one. This is the first one. It's already constructed here with you. This is 3 angle bisectors. 3 angle bisectors on that circle, on that triangle. And where it's concurrent is a place called the incenter. Okay, place called the incenter. Okay, quick review. Also did this in Thursday's class. Okay, the word concurrent. Okay, definition of concurrent lines. This should also be in your notebooks. Definition of concurrent lines. Those are, well, here it is. Angle bisector there, angle bisector, angle bisector there. What do you notice about it? Well, they all meet in one particular point. Okay, and that point is called the incenter. Okay, so if 3 lines, so the definition of concurrent lines, those are 3 or more lines that pass through the same point. So we know if they're passing through the same points, those are intersecting lines. And we know that from first semester that any 2 lines will intersect in exactly one point if they do intersect. That one place is the only place that this angle bisector, this angle bisector, and this angle bisector will pass through. And here's the neat part, okay? The incenter here, what makes it special? The incenter special. So this construction is special because if I did it correctly, I could inscribe a circle within that triangle, okay? So remember, angle bisectors from first semester, angle bisectors, if you're a point on the angle bisector, you're actually equidistant from the sides of an angle. Remember that? We proved that last semester? So it's here, if I do my construction correctly, that angle would be congruent to that angle. So all these points right here would be the same distance from that side and that side. Okay, and remember we measure distance as the length of a perpendicular. Okay, so here would be the same. And why would I know that? Well, SA and SAA, I believe. Oh, sorry, yes, SAA, right? SAA if I drop the perpendicular. Okay, so not really worried about that, but what I know, okay, to actually kind of do it here, if I dropped a perpendicular here, okay, it would be the same as if I dropped a perpendicular over here. Okay, why? That point is equidistant from that side of the angle and that side of the angle. Why? Well, it's on an angle bisector. Any point on a bisector of an angle is equidistant from the sides of that angle. That was a theorem from last semester. It might be worthwhile reviewing, since this is why this is going to work in a second. Okay, so notice here, I draw in a congruent segment there, because I know that these are equidistant because they're on that angle bisector. Let's look at this angle bisector right there. I know that this angle bisector right here, this point has to be the same distance from that side of this angle as this side of this angle. So if I dropped a perpendicular in there, I would have known that those 2 lengths are the same. Okay, those 2 lengths are the same here. And this one here also has the same length as that one. So all 3 of those lengths should be the same. Okay, so here's the fun part. If I have the distances to these 3 sides right here is the same. Here, I have 3 points that are equidistant from a fixed point. What can I draw? Well, I can draw a circle, and that circle is going to be tangent to all 3 of the sides. And this is only going to work, right, the way that we did this so far. I actually have to construct the perpendicular, but this is an isosceles triangle. We did this in an isosceles triangle last week here. So let's check this out. If I can get it to work. Oop, I need to push this down a little bit. Let's see if we can get it to work. Oh, it's really small. Here, spin it around. There we go. That looks pretty good so far. Messy, messy, messy. But you get the idea. I think this is pretty successful. I'm going to give myself an A- on this one. And completed. There we go. Pretty ugly as we got there, but hey, actually that's better than usual here when I'm doing it in front of the board here, okay? So angle bisectors, what is it good for? Finding the incenter. And what is the incenter? What makes it special is that allows us to inscribe a circle within the triangle. Okay, when I say inscribed, you say inside, okay, inside the triangle, okay? And then the center is at incenter. The center of the circle is at the incenter, the center of the inscribed triangle. That's what inscribed circle. That's why we call that the incenter here, okay? So where it coincides, where those 3 points, 3 lines coincide, they're at the point where they're concurrent, that forms the center of a circle that you get inscribed in that triangle. Pretty neat, okay? The neater thing, though, in yesterday's class, the neater thing was coming up with a centroid, okay? So 3 angle bisectors, what's it good for? It finds the incenter, gets us an inscribed circle because, that point's equidistant from the 3 sides of the triangle, right? You know that because they're angle bisectors. But anyways, the next one was medians, okay? So the median construction I don't have up here. For the sake of making this video kind of short, we'll just kind of fill it in there. So medians, remember medians. That's the one where, like the angle bisectors, we start from a vertex, but where do we draw to? It's a median. Well, I would need to perpendicularly bisect this side because I would need to find the midpoint. Remember, median. Median is vertex to midpoint of the side opposite. Okay, midpoint of the side opposite that vertex here. Okay, so this median, what started this vertex here, it's going to have to go to the midpoint of the side opposite. And I'm just estimating there, but how would I construct a midpoint? That's right, you use perpendicular bisectors to actually find, like, if you perpendicularly bisect this line, well then, the intersection of the perpendicular bisector and the line, well, it's got to be the midpoint of the side, okay? So I'm just estimating this, and I'll just maybe draw it in real quick here. Vertex to midpoint, well, let's just maybe estimate this here, and then again, I won't spend time doing the construction because I don't want this video to be too long. Vertex to midpoint over here, well, check it out. They're concurrent as well. And what's special about that is if I laid it flat, gravity-wise, that's my center of gravity right there. And what's it called? Well, other shapes have this. That's why it's an important thing to get, because you might study this in the future if you're designing things about where to balance certain things or where to prop up stuff if you're building a table or something like that. What you're looking for is called the centroid. Okay, the centroid here. That's your second special center of a circle. Okay, so centroid. How do we get it? What finds us the centroid? What finds us the center of balance? That is medians. Construct 3 medians. You need to do the perpendicular bisector, connect the vertex to the midpoint that you found with the perpendicular bisector construction. Gets us the centroid. And what makes it special? What makes the centroid special? Well, it's what I showed you earlier, which was it's the center of balance. Here. So they kind of fell over because I have a twisty marker right there. But here's my centroid. If I have it right here, look, in this one here, I showed this to you. Centroid was very close to my incenter, but if I use the incenter, it just falls right away. I do the centroid, perfect. Good to go, we balanced it here. Okay, center of balance. Okay, last thing that should be in your notes, okay, I only got a couple minutes before class starts here, is what 3 perpendicular bisectors get you. Okay, this is a fun one here because the perpendicular bisectors are also going to get you a circle. Okay, it's going to be concurrent at a place called the circumcenter. Circumcenter. What do we notice there? Okay, incenter, circumcenter. In for inscribed. You got it. In for inscribed here. Circumcenter, circum for circumscribed. Circumscribed. Okay, so I construct 3 perpendicular bisectors, and I have that kind of shown right here. I constructed that one, then I just drew that one in because I knew it would have to pass through there. That intersects where? Is it concurrent? How do you know it's concurrent? It's concurrent because, yes, those 3 or more lines, they intersect at exactly one point. Okay, so what this point is called the circumcenter. Circumcenter, centroid, incenter. Perpendicular bisectors, what are they good for? Finding the circumcenter here, okay? So it was a little bit hard for me to explain in class yesterday, but the idea of this is, well, let's think of this perpendicular bisector, okay? We perpendicularly bisected this side. That's why you see a point above and a point below, point above and a point below, that are each equidistant from these endpoints, right? Each equidistant from these endpoints here. I use the same radius on this endpoint here to draw that arc as I did on this arc here. That's why this point here, same radius here to here and here to here will equal lengths, right? Equal lengths here. That's true of any point on a perpendicular bisector. It's equidistant from the endpoints of the segment. So that being said, this point down here on the circumcenter itself, well, it's on this angle bisector. So what do I know? Since it's on this angle bisector here, that it's equidistant from that endpoint of this segment as it is to this endpoint of the segment here, okay? I happen to draw a special special triangle by mistake. What triangle did I draw? This is a right triangle. That's a right triangle here. So that's why my circumcenter is actually on the hypotenuse. We might talk about that a little bit later, okay? But anyway, the point is that where the perpendicular bisectors meet, well, this perpendicular bisector meant it's equidistant from the endpoints of that segment. Well, this construction here, I constructed this perpendicular bisector. So what do I know about all these points? This point right here, for instance, is the same distance from the end point there as it is from there. I use my radius. I didn't change my radius. This and this are the same, just as down here, this and this are the same. And you know what? Every point, okay? So an alternate definition for a perpendicular bisector is the set of points in a plane that are all equidistant from the endpoints of a segment, okay? The endpoint segment here. So what I know is, not just that this point here, because it's on this perpendicular bisector, is equidistant from those two endpoints. I also know that because it's on this perpendicular bisector that, here we go. This point here is equidistant from that endpoint just as it is from that endpoint because it's on that perpendicular bisector. And you know what? If in step one I proved that here and here are the same lengths, then I would know that, and I knew that here and here are the same lengths, then I know that these two lengths would have to be the same here too, okay? So the perpendicular bisectors intersect in a point that's equidistant from the endpoints, from the vertices of the triangle you drew this perpendicular bisector. So what does that tell you? Well, we just came for a chapter about points being equidistant from a fixed point. That means what can I draw in? A circle here, okay? And I actually here, I'm a dummy the way I set this one up, or maybe I'm just working fast here. I can't draw my whole circle right now. Why? Well, I just don't have enough space. Okay, so let's check it out here. That distance to the vertices, that's just going to be a radius of a circle. Here, fell off a little bit here. There we go. Okay, a circle. Here, a little bit too low here. So look at that. That's pretty good. I give myself an A- right there. Okay, so this is the circle here that inscribes that triangle, okay? Because this circle is circumscribed about that triangle, okay? Remember, when I say inscribed, you say inside. That circle's inscribed in that triangle. So that means when I say circumscribed, you say outside. That circle's outside of that triangle right there, okay? So circumcenter forms the center of a circle that will intersect the three vertices. And I'll just write that here, and then this video is done. Find center of a circle that passes through all three vertices. And that is that. I yield the room to Mr. Lee to teach the little calculus here. Mess me if you have any questions, guys. Get that in your notes. Get that table in your notes. Check it out here. And hopefully you follow the logic. Bye, guys. Have a great spring break.